All right, welcome. We are pulling out the in-class worksheet, in-class problems from yesterday on problem number 8. Problem number 8. So I know we have this one set up. I know that is already what we did. I do just kind of want to walk through that rationale again with you. I want to reinforce the ideas of this problem sheet, the problem type sheet, and kind of working through this. And maybe hopefully I made it kind of clear, but these are kind of a yes-no. Is it a 1D motion problem? If the answer is yes, then we put this stuff in. If the answer is no, we don't put this stuff in. If the answer is yes, we do this. If the answer is no, we don't. And we only did through the first 4 points because that's all the further we are so far. So we take a look at in-class problem number 8. In-class problem number 8. We read through it yesterday, and I know we already picked the equation, so we'll kind of go through this again. But it says an apple falls 3 meters out of a tree and lands on Sir Isaac Newton. How fast was the apple going when it hit him on the head? And we're going to kind of stop there, and we're going to pretend like that second question doesn't exist yet. So again, this problem type sheet is meant to be helpful in setting these problems up. And it's kind of a series of yes-no. So is this a yes-no problem? I'm sorry. Is this a 1D motion problem? Yes. So we got to make one of these 2 lists. Which one are we going to make? The y or the x?
The y.
Why the y? Vertical, right. So we're going to make this list of variables. Okay? So we're going to make camera, don't worry, I'll pan for you in a moment. Okay, so yes is a 1D motion problem. Yes or no? Is this a constant velocity problem? Does it say that the velocity is constant? Or does it say that the acceleration is 0?
Yes.
No, it does not say that, right? So we don't put that in. Don't. Okay? It talks about an apple falls from a tree. It doesn't say like moving with a constant velocity. It doesn't say the acceleration is 0. It doesn't say it's not accelerating. Don't put that one down. Does it say, is this a free fall problem? Is the only gravity acting on that apple gravity?
Yes.
Yes. Because we ignore air resistance, that's the thing we can just kind of pretend doesn't have a big impact, which if we're not falling like crazy, crazy high distances, or it's relatively heavy, it's an okay approximation. So if that is the case, then we can acceleration is equal to negative g, and on Earth, and it's on Earth, unless I very specifically tell you otherwise, on Earth, the gravitational acceleration due to gravity is negative 9.8 meters per second squared. What is that negative? What's that negative telling me?
It's going down.
It's going down. It's accelerating downwards. Okay, it's accelerating downwards. Not that it's moving downwards per se, but gravity is causing it to accelerate towards the Earth, downwards. Is this, yes, no, is this an object is dropped or falls type of problem? Does it say something is dropped, or does it say something falls? Yes, it says an apple falls on Sir Isaac Newton's head. So therefore, my initial velocity is going to be 0. And that's where we're stopping right now because we haven't talked about max height problems or anything like that. Okay, then oops, I should go back. Now we go back to the problem. Sorry, camera, you can't see it anymore. Apple falls 3 meters, how fast? How fast? Where's my question mark going here? That's our final velocity, that's our question mark. And where's that 3 meters gonna go? Is that a displacement or time? That's really all that's left, remember.
Displacement.
It's a displacement. Meters is a measure of displacement. Okay, now remember displacement is a vector, which needs a direction. So which direction is this apple going?
Down.
It's going down, so this needs to be a negative 3 meters. I know we got it that far set up yesterday. Yesterday we also went through and said, hey, we don't know time, we don't care about time. That's part 2 of the question. So if we look at which equation doesn't have time, we can cross it off. And then we can say, well, equation number 4 doesn't have a time. Notice how in equation number 4 I wrote delta y instead of a delta x, because there is no delta x, it's a delta y. This object is moving in the y direction, in the y direction only. And that's where we ended yesterday. So it's kind of a recap, kind of walking through the rationale, why do we do what we do? And now we plug in numbers. So my initial velocity, I like to take care of my zeros kind of first. Is 0, so 0 squared cancels that whole term out. My final velocity squared is what we're solving for final velocity. That's my unknown. Is equal to 0 times 2 times negative 9.8 times negative 3. Negative times a negative, 2 times is a positive, right? So 2 times 9.8 is 19.6 times a negative 3 is going to be a positive. Bf squared is equal to 58.8. Is that my final answer?
No.
No, right? Because it's not Vf, this is Vf squared. I don't want squared. How do I get rid of that squared? Good, square root. Okay, so we take the square root of my answer and we get a number. Now before I write that number, I want to ask you this. What is the square root of 4?
2.
Plus or minus. Remember we talked about that and you said, hey, we're going to come back to that. It's plus or minus 2. Okay? The square root of any number is plus or minus. So mathematically, this answer is plus or minus 7.668. So if we round it to 2 decimal points, it's plus or minus 7.67 meters per second. Anytime you take a square root, you have to make the choice. Is it going to be the positive or is it going to be the negative? Now, what does a positive velocity tell me? It's moving in the positive direction. So if we were talking horizontally, which direction would it be moving?
Right.
To the right. What if we're talking vertically? Now it's moving up. Okay? What is a negative telling me? Horizontally it'd be?
Left.
And y direction?
Down.
Down, okay. Now we have to make the choice. Which one is it? Is it the plus 7.67 or is it the minus 7.67? Because the apple is falling on his head, it's going down. So we have to choose the negative here. That's why it's a negative. A pretty common math mistake is we misidentify this delta y. And I'm going to erase this and I'm going to put it back because it's wrong. And I don't want it to stay there. But an incorrect math error starts with saying the apple went 3 meters. And if you say the apple went 3 meters, then this becomes the square root of negative 58.8. And what happens when you type that into your calculator?
You're going to get an error.
You get an error. It's not possible, right? You get some imaginary number. Isn't that what happens when you take a square root of a negative? You get an I, right? This is physical. You don't have eyes. So if you get to this point, you mess something up somewhere. And go back and try to figure out what you did. People just conveniently be like, oh, the square root of negative 58, error, oops. Forget about that negative. It must have just been a positive. And then because that was a negative, they put that negative there. That's not why that negative is there. Okay? It's there because, it's not there, let me rephrase that, because this went down, this went down, which makes that a positive. This is negative because that tells me the object's direction of motion is down. That was something we had to choose. That's something we had to pick. Okay? Now there is a part B, or second part to this. How long did it take the apple to fall? So if we say, well, I talked about this the other day. I talked about a best practice approach. The best practice would be well, let's pretend that we don't know this, and now let's solve for this. This is a rounded value. If you use that rounded value in another equation, you get an even more rounded value. So the best approach would be to say, let's pretend I don't know that one. So we would then use equation number 3, delta y is equal to vi t plus 1/2 a t squared. And my initial velocity was 0, so we can go through and we can go through and we can plug our numbers in here. My delta y was -3, 1/2 a, oops, 1/2 times -9.8 times t. -3, -4.9 times t squared. How do I get t squared by itself?
Divide.
Yeah. Okay, we want to get rid of the -4.9 first. Okay? Don't take the square root. It's possible, but most people screw the algebra up, so don't do it. Divide by 4.9. So if you take -3 divided by -4.9, we get 0.6122, blah, 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 blah. So that's what we get. Now, when I take the square root, I wrote down, because I'm lazy, I only wrote down a couple of digits, but on my calculator, I have lots of digits. So I can take the square root of my answer, and it's going to keep every single digit that it has to get me my best non-rounded answer. And I also do, if I have a variable on this side, when I do my final answer, I always put my variable, I just switch it. Okay, so I'm now taking the square root, and now I'm going to say t is equal to, instead of the number equals to, it's the same thing, but this is how I like to write it, is 0.78 seconds. Now, what's the square root of 4?
Plus or minus.
Plus or minus. So what's the square root of 0.612 is going to be a plus
A plus.
or minus 0.78. And now we have to make the choice. Time's a little different though. Because if I'm using a stopwatch, on your mark, oops, I just reset it, right? Reset. On your mark, get set, go. Can I have a negative time? Right, my stopwatch starts at 0. The time frame I'm talking about starts at 0, so I can't have a negative time. So for our time, it's gonna be the positive. It'd be before the event happened. Because it's a square term, so it's really parabolic in nature, but it'd be before we started the stopwatch. All right, questions on that? I want you to read through question number 9, and I want you to go through the problem types, and I want you to make a list of variables. Okay? Problem number 9 says a penny is dropped from a parking garage and strikes the ground. It strikes the ground in 0.96 seconds. From what height was the penny dropped? That's the problem. There's one number given, there's one question asked, and using that yellow problem type sheet, make a list of variables. And if you kind of stop, I'm going to ask you just to kind of stop there. We can kind of check our work to make sure we're on the right path before you keep going. So go through the problem types, and based on your problem types, make a list of variables that is given in the problem, and you can pull from your from the problem itself. Okay, I'm going to give you about 30 seconds, probably about 30 seconds, because all we're doing right now is we're making a list. So all you're doing is you're making a list based upon number given and problem type. pause once you get that list, it'd be good, just so we can kind of check and make sure we're on the right path. Thanks, Mark. All right, let's go through. A penny is dropped from a parking garage, strikes ground in 0.96 seconds. From what height was the penny dropped? Okay, so is this a 1D motion problem? Yes.
Yes.
Okay, is it X or Y 1D motion problem?
Why?
Why?
So this is going to be a delta Y. Okay, so delta Y, the idea A and T. Is this a constant velocity problem? Is acceleration equal to 0? No.
No.
No. Okay, so nothing from there. Is this a free fall problem? Is the only force acting on the penny gravity?
Yeah.
Yes. So because of that, what can we fill in?
Acceleration was negative 9.8 meters.
Yep, negative g, and on Earth that value is negative 9.8 meters per second squared. Keep in mind that the only time we would say it's not on Earth is if we very specifically say it's not on Earth. But otherwise we'll say it's 9.8. Is this a dropped or falls problem?
Yeah.
Yeah. So what can we fill in?
The initial velocity.
Is going to be 0. Okay? Now, that's it for problem types. It's not a max height problem. It's not a delta y is equal to 0 problem. We'll get to those later. 0.96 seconds, and from what height? Where do I put my question mark? Where do I put that 0.96 seconds?
We put 0.96 in the time.
Where's my question mark?
Delta Y.
Delta y. Okay? There's my delta y. So now, girls, but you're talking about. Okay. So while we go through and we cross off final velocity because they don't care about final velocity, it's a drop problem, we can go through and say, what equation are we going to use? And what equation doesn't have final velocity in it? Equation number 3, which is delta y is equal to vi times t plus 1/2 a t squared. Give you, I don't know, 30 seconds, plug in your numbers, solve for number 9. This is problem number 9. Plug in your numbers, solve it, and then we'll talk about your results, because your number is going to be slightly different than the question and the answer stated on the worksheet. So let's go and talk about this. Okay. This is equation number 3. Because my initial velocity was 0, my my VI times T is 0, that whole term cancels out. And that's equal to 1/2 times A times time, and we get a value of negative 4.52 meters. Now, I want to emphasize a few things. What object was going 0 meters per second? The penny. The penny was moving 0 meters per second initially, right? What object was accelerating due to gravity at negative 9.8 meters per second squared? The penny. What object fell 0.96 seconds? The penny. What was the displacement of the penny? The penny went, what does this mean? Down. It went down 4.52 meters. What did?
The penny.
The penny. Okay, I'm trying to make that point. The penny went down 4.52. So with negative 4.52. But, notice how on the answer, it doesn't say negative 4.52. It says 4.52. And this is somewhat semantics, but it's making sure we answer the question. If we have this building, and we have a penny, the penny went down, delta Y went down 4.52 meters. The penny went down 4.52 meters. But the question isn't asking how far did the penny fall, right? It doesn't say how far did the penny fall. It's saying from what height was the penny drop. So it'd be the same as like, what is the height of the parking garage? Did the parking garage accelerate down? Did the parking lot start at this? Did the parking lot fall for this? Remember, this is a list for the penny. And yes, the penny went down. But if I'm going to go and measure what is the height from here to here, my height is a positive 4.2 meters. We have to use the penny's drop to determine the height. I just watched a video last night, actually, on Mark Rober. Have you watched him on YouTube? Okay. He's a former NASA engineer. He worked on the Mars rover. Now he's, I think, just an all-time YouTuber. But he designs stuff. I don't know. My kids found him a while ago. I'd seen him before. But like 5 years ago, he posted a video that I just watched. And it was, I think apparently at the time, people were jumping off of the cliffs, and they were like, oh, like a 100-foot cliff, something like that. It was like he was talking about these 100-foot cliff jumps. And it was like, how could I figure out the height of my cliff that I'm going to jump off and post on my social media? I don't think TikTok was a thing 5 years ago, so whatever that was at the time. And he said, well, we can actually just use this equation, right? Because if I jump off of a cliff, I just jump off, my initial velocity is 0. This term cancels out. And if I time, like just use a stopwatch, start, stop, if I can time how long it takes for me to hit the water, then I can figure out indirectly, right, I find how far I went down, but then we could determine the height of the cliff. So he developed an app that it was just a stopwatch that used this. It had this formula running in the background, and when you hit stop, it spit out a number. But he didn't use meters, because we're in the United States and we're better than everyone else in terms of this metric system. We don't need that metric. So instead of using 9.8 meters per second, he used 32 feet per second squared, because that's the acceleration due to gravity in feet. So he was able to do that. But the idea is you can use this equation with it, as long as you just drop. You just drop it. And if you time it, you can then determine heights of really tall things, assuming that air resistance is negligible, right? So if I was on the top of the Grand Canyon, I don't know how they feel about doing this at the Grand Canyon, so I'm not saying, let the record show that I'm not saying you should actually do this, but hypothetically, if you did drop a pebble off the top of the Grand Canyon, and all you'd have to do is use a stopwatch, and once it hit the ground, you could then calculate what is the height of your Grand Canyon. Okay, or whatever else you wanted. You know, like, oh, how high is the building? Let's drop something off and measure it. And it's gonna be pretty close. It's gonna be pretty close. At some point, it's an accuracy of like stopwatch thumbs, right? But that's the idea, that's the intent. You can use this. But indirectly, this is, remember, this is how far the object went down. So the opposite of it is the height from which it was dropped. Just be aware of that. Okay? Questions? These problems are a little bit different because they have gravity. I think all of our problems so far are going to be dropped. But they don't have to be, right? I can take this ball and I can drop it, and that's true. But this is true even if I throw it. Because once it leaves my hand, what's the only force acting on the ball? It's gravity. Now, it's going to get to the ground quicker because it has an initial velocity, right? It's now going like 5 meters per second. So it's going to take less time because this is a different number. But once it leaves my hand, it's a free fall. It's still a free fall. When it's in my hand, then it's not, because I'm pushing on it. Okay? People they think, well, you threw it, so therefore there's more forces. But once it leaves my hand, my Jedi mind trick, no, that's not a mind trick. My Jedi powers are not that strong to affect the midichlorians that I can't keep accelerating once it leaves my hand. I haven't learned that ways of the Force yet. The Force. Star Wars. Star Wars reference, everyone, just for the record, in case you didn't know. I don't know why you wouldn't know, but. Okay? So, time left. We have some. There is a worksheet called Fab 5 that I'll put right there, and you can get up and grab in just a second. You're going to get started to work on it today. I will give you some class time on Monday to work on it too. It's not officially due until Monday evening. That's a mixture of motion in the X direction and motion in the Y direction. If you haven't finished the worksheet called Constant Acceleration Problems, I would suggest you finish that first before you move on to that one, but we should be making progress forward. That's going to be, we'll do a couple other things on Monday before I let you go and work on that again, but that's we'll kind of split our time between today and then on Monday for some work time, and anything you don't finish on Monday then will be your homework on Monday. So depending on how much progress you make today and on Monday, may or may not be homework. So you can grab that. Any questions you have, please ask and get this taken care of sooner than later.